welcome our next speakers, Joseph and Ilya, who will be talking about how bootloaders are broken and how to sort of look into them. Please give them a warm round of applause.
Hello, does this sound okay? Okay, cool. Welcome to Boot2root, auditing bootloaders by example. I'm Joseph Tartaro. I hack things for IOActive, and this is my second time at Congress, so I'm really excited to be back here.
Hi, I'm Ilya. This is my 18th or 19th time at Congress. Happy to be back here too. I've spoken here, I think, 7 or 8 times before. And I'm very excited to speak here together with Joe. We've been working together on bootloaders the last year and change. And this is, minus the NDA covered stuff, this is some of the things we've observed and seen. So I'm very excited to do this.
The expected audience for this talk would be embedded systems engineers, security people who are interested in embedded systems, and just curious security people. Just a caveat. We're going to be quickly going through about like 70 slides or so, and a lot of it's just like examples of C source code. So if you did not realize you were signing up for an hour of that, feel free to walk out. We're not going to be offended. And then another caveat would be, this isn't really trying to flex and show, look at all the bugs we found. The purpose of this was to kind of show people, hey, if you have not looked at bootloaders before, this is our recommended areas of attack surface that are interesting. This is probably where you should get started. And then some examples of nobody's really looking at them, and they should start. So that's pretty much what's going to go on right now. So quickly, here's the agenda. We'll discuss quote-unquote bootloaders, why they're important, some of the common ones we looked at, attack surface, and our conclusions. So there's going to be a wide interpretation of bootloader. So basically what we mean by that is anything that's in your secure boot chain. And if you don't have experience with these, or you haven't looked at them much, you can kind of think of it like from an operating system standpoint of user land calling into kernel space. You'll have like kind of normal world calling it to secure world and stuff, and that's kind of what you're looking for is those pivots and when they're processing, attacker or user controlled data. So why? Because they're, critical for security. It's a key component of your chain of trust, and it's very obvious that a lot of device designers are poor at hardening and limiting attack surface. And what we mean by that is a lot of the devices we've looked at over the last year or so, you'll find devices that have like full network stacks, even though they don't need a network stack. You'll have a bunch of code loaded up to handle file systems that are never expected. So it doesn't really make sense why they're not limiting all that attack surface. There's also a huge underestimate of reverse engineering. People just kind of assuming that there's no bad actors and nobody's really going to look at this thing, and it's this hidden black box that we should ignore. And a little story behind the presentation is we're actually on a train going to a baseball game. I was trying to introduce Ilya to the lovely game of baseball. And we were talking about U-Boot, and I pulled out my phone and we went to the U-Boot GitHub, and in about, 10 minutes, 15 minutes, we ran into like 10 bugs, and we went, yeah, we should probably audit some of this stuff. And kind of inspiration from a previous talk that Ilya has given at Congress where he audited a bunch of different BSDs. I said, why don't we look at a bunch of different bootloaders? And just to give credit where credit's due, we are not the first to look at any of this stuff. So this is a list of people that kind of inspired us, have done really interesting work. And we recommend if you're interested in any of this and you enjoyed it, you should go check these people out and see things that they've released in papers and stuff like that. So where are they? Bootloaders are pretty much in everything. You have your workstations, phones, game consoles, your TV, everything. And generally the security basically depends on this. So it obviously really, really, really matters. And so with that said, we basically started looking at these common open source bootloaders. So, U-boot, Core boot, Grub, CBIOS, Cafe, which is Broadcom, iPXE, and TianoCore. And we're just looking at what's on GitHub, what we downloaded. Obviously, in your real-world scenarios, the devices that you have at home or go buy and start looking at, they're going to be heavily modified. They're going to have weird custom drivers that aren't available, things like that. So, we're not here to argue the likelihood of some of the bugs we found. We're not going to argue exploitability. Half of them we don't know if they're exploitable. We
will for one.
Yeah, we will for one. We don't really that's not really the point of it. The point is to kind of show people, show designers what they should be concerned with, and show interesting or researchers that might be interested what they should look at. U-boot is extremely common. It's in a ton of devices. There's a huge, very customizable config for all different sorts of boards and stuff. There's concerns for environment variable stuff. There's a super powerful shell. So you'll sometimes see even shell injection concerns based on environment variables. It's pretty funky, and there's lots of drivers for tons of devices. So it's kind of a great first step of looking at something that kind of covers a huge breadth of things. And so features of U-boot that are interesting would be network stack for different protocol parsing, file systems, and they also will load their next stage images from all sorts of weird archaic things that nobody uses anymore. And it's just used by tons of devices. And then Core boot, and I apologize, this is a little dry right now. We'll eventually get to stuff, but Core boot, it's more targeted towards modern operating systems. There aren't legacy BIOS support. It actually, they took a methodology that other projects don't, which is they're not going to implement features that they don't want to. So if you're trying to do network booting or something, you use Core boot to boot into iPXE or something. They're not going to implement that feature. These are used in Chromebooks, and obviously some of the interesting parts come from Google. And one main interesting area is SMM. And then Grub, obviously you guys are all familiar with this. The primary concern here is multi-boot spec, and they support just a ton of file systems, so that's obviously the attack surface you'd be concerned with. But the interesting part here is that there are UEFI signed versions of Grub. So that's kind of like your secure boot break right there. If you find a vulnerability that's an assigned version, you can now load that into your UEFI and exploit that vulnerability, and you're good to go. And then CBIOS is the default BIOS for QEMU, KVM. This supports legacy BIOS stuff, so you'll see that this gets booted into from things like Core boot. This supports TPM communication, so that's kind of interesting. And it's the compatibility support module for UEFI and OVMF. So. And then Broadcom Cafe. So this is used in a ton of different network devices and TVs and stuff like that. And the obvious attack surface there would be network protocols, the network stack. That's what you'd want to look at. iPXE, this would be more network-based stuff, various parsing, and similar to Grub, there's UEFI signed versions. So it's a great potential pivot for secure boot stuff. And then finally, TianoCore. There's really no introduction needed here. There's been a ton of great presentations over the last 15 years of people just doing everything to this thing. And due to that, since it's pretty much the most scrutinized one out there, it's really mature compared to everything else. So when you bash TianoCore, realize that it's way better than everything else. So, and there's a lot of implementations built on top of it, like platform-specific stuff, Qualcomm's ABL and XBL, things like that. So you'll have all these, you have the base TianoCore EDK2, and then you have all the custom stuff built on top. And then related to bootloaders, you have things like trust zone, and that's kind of where I mentioned you have like normal world and secure world. You'll have these interesting pieces of code that are running into those secure areas that you're going to want to look for, pivots into there so you can gain access to secrets. And then, and obviously from the host operating system, the attack surface there would be you can modify things like Nvram. So you can set variables that when the next time you reboot, the bootloader is going to process those variables. So. And this slide's more for reference. Later, you can get the slides or take a picture or something. These are just links to some instructions for building and whatnot. So if you wanted to start looking at these, you can quickly build a little environment and poke around. Just really quickly to go through, the concept of secure boot. You kind of have your chain of trust. You'll have the boot ROM that will then verify and load various other loaders that then verify and load the next thing. And you'll sometimes have a TPM involvement. You'll have some trust zone involvement, and then OS interaction stuff like the OS. Basically setting things like Nvram, which will set boot configuration stuff, whatnot. So the boot ROM itself is something you've probably seen the talk by Cordy Oriup, I think earlier it was. It's really important because it can't be patched. It's a hardware revision would be required if a vulnerability is found, and it's so early in the stage, and you would basically compromise everything after it. That is where you'd want to go. It's extremely bare minimum. It does some initialization of hardware and memory stuff, and then you'll find things like maybe implementations of fast boot. So you have a USB stack, so that's obvious attack surface you'd be interested in. And then it will, verify the signature of the next stage, and then boot that. And then you move on to the next stages, and this is where they start initializing the rest of what's necessary: network stacks, SMM handlers, and whatnot. And they'll basically just keep handing off. And then you'll run into things like trusted boot and measure boot, which is a verification and then measuring, which is kind of more for logging and whatnot. It doesn't actually mitigate anything. It just kind of alerts you of stuff. So. Some hardware environments are a little different, like the secure world stuff. You'll have ARM with trust zone. Windows has VTL0, VTL1, hypervisor stuff, and then, I'm basically repeating myself. And then eventually the operating system, that's going to get, the kernel's going to be loaded, it's going to be verified, and then eventually start running, and then you can have fun. So early observations is everything we pretty much looked at that's open source. There's no privilege separation. So if you were to compromise a piece of component, you pretty much rule everything. And what's interesting is there are some proprietary bootloaders that you're starting to see, like Apple, for example. They're doing some aspect of privilege separation. So if you were to exploit a portion, you didn't necessarily control the world. And right now, at least all the stuff we looked at did not have anything like that, but maybe in the future, we'll see that. So this is the list of the attack surface that we think people should be interested in and focusing on. You have Nvram, file systems and files, all network stack protocol stuff, all various buses, SMM, DMA, and hardware stuff. The interesting thing about buses that we've noticed is that embedded designers seem to inherently trust anything that an end user should never interact with. So they go, okay, an end user uses USB, so we should verify some of that, but they do a bad job. But an end user doesn't play with SPI flash, so just inherently trust it. Or an end user isn't the TPM, so just if the TPM says something, run with it, and they mess it up a lot. So Nvram, these are the various environment variables that can be configured, for the next boot cycle. And like I said, it's basically processing of user-controlled data. So if you start looking at some of these bootloaders, here's the interesting functions you'd want to look at. For example, in uboot, you just kind of call for environment get, and grep through, and you see them grabbing the environment variable and see what they do with it. If they're not doing any sort of validation, you're going to hit a bug. And so an example of that would be right here. You see there's an environment git for bootp VCI. It checks if it existed. It will then do a stir length and then just mem copy it directly into a buffer without validating that it can fit the buffer. And this is actually kind of funny. Earlier today, we were like, we should try to exploit one of these just to show it. So we toyed with this one, and just threw a bunch of bytes, and it starts just kind of sending these weird packets over the wire, and a bunch of bootp stuff. You'll see later on, you just have full raw packets of whatever payload we send, but it wasn't very realistic. It kind of started getting into like the QEMU network implementation stuff. So we kind of avoided and moved on to a different bug. But as you can see, it's very, very easy for you to start looking at this stuff and being interested in it and quickly set up an environment and mess with exploitation. And we'll get into it, but there's no mitigations. So as you see, there's a bit of a pattern here. Environment get hostname, mem copy with stir length. No checks. 128 byte buffer, environment get with boot dev, stir copy. Bootfile, stir copy. It just keeps happening. This is kind of what we were talking about. It's just the quality code is not very great. This is what's funny is when we were messing with that bootp VCI stuff earlier this morning, we went, this is going to be more involved. So Ilya was like, well, let me just go find a different bug. 10 minutes later, he's like, I found a different stack smash. Okay, let's work on that one. It's just like this is a perfect example. They environment get the variable, then they'll grab the very first element of that variable as a length, and then they use that as a length. And yep. And it keeps happening. So just a quick example. See this. So the attack scenario of this would be you have a device, you have Nvram that you can physically modify because you have physical access. And this is kind of an example of the default Nvram. So we just threw an environment variable with 600 bytes, and you'll see towards the bottom there's 4 bytes where we threw a function in there, and that's the address. So just this had to do with the JFS2 file system loading. So you just do fs load, and it's done. So,
that's shellcode being executed.
So this is. Sorry, I can't see. So obviously, if you've never looked at this stuff, it's kind of fun to play around with, and you should start poking at it because why not? And screenshot.
Sweet, cool. Okay. Cool. So that was the Nvram attack surface, which is usually the most fun to play with. Programming the spy flash sometimes may take a little bit of fiddling, but in terms of attack surface and fun things to play with, it's as Joe said, often overlooked, and so it's easy to toy with. And so you saw all this sprintfs and mem copies and string copies. So there's a lot of fun there. But obviously, there's not just Nvram. There's more attack surface to sort of a trusted boot environment. And obviously, one of them is the file system, right? Because this thing needs to boot, and it needs to find images, and they're stored somewhere, and your file system sort of brings order to that chaos. And so basically, you need to mount your file system. And often, file systems are not signed or integrity checked, or not all of it is. Because before you can do that, you need to be able to read something, right? And so obviously an example of a common file system would be FAT file system. If your boot environment supports loading your USB drive and for storage, it's probably going to be FAT. Depending on, and the flash itself may have its own proprietary format, or it may use X2 or something else. But clearly the file system parsers, that's prime attack surface. Closely related is obviously the files inside of your file system, right? Now, depending on what your boot environment looks like, some of these files are going to be integrity checked, but some of them might not be, right? And so those file parsers are interesting attack surface. And if you're either looking for bugs or you're building a product, we would highly recommend fuzzing these. And it's like starting with AFL is probably a good starting point. But we'll show some examples of some bugs we saw in a number of bootloaders. So we'll cover X2, we'll cover a bitmap splash parsing one. I think the other ones are just sort of examples of where there could be bugs, but those two we'll cover. So this is grub, and this is grub X2, and grub X2, this is the symlink code. So it looks at the file system and it goes, oh, okay, this is a symlink. How do I parse a symlink? And so the symlink says, hi, I'm a symlink, I'm this big. And what grub does is, oh, great, I'll allocate that much size, but I'll do one more for no byte. And of course, that is a classic integer overflow. And the grub memory allocator actually returns a valid pointer for a 0 size. So this is a perfect primitive. So you get a pointer to something that is of 0 size. And then it actually reads the symlink content from the file system into a 0 size buffer. And obviously that's going to cause memory corruption. And the primitive, you can't see it here, but the primitive is really nice because that particular read function actually, if there's much more than disk, it stops reading. So even though you can say read 4 gigs, you can make the layout so it only reads, let's say, 1,000 bytes or 100 bytes. And so you have this near perfect primitive to cause memory corruption. This was in Tiana Core, for example. This was the bitmap splash screen parser. And I don't know if you know anything about bitmap internals. It's a very simple format, but basically you can have a 4-bit bitmap, and that gives you a palette of 4x4, which is 16 bytes. And so the idea is if you have a 4-bit bitmap, then it has a 16-byte palette, and so it goes and reads that 16-byte palette, except you tell it how big the palette is, and you can say, okay, I know you're expecting a 16-byte palette, but I'm giving you a 256-byte palette, and it'll read it into a 16-byte buffer. So that was broken, and then for the 8-bit bitmaps, similarly, it was broken the same way. And this is just the tip of the iceberg. There are many, many, many more. This did not take long to find. But let's move on. Obviously, okay, now that we've looked at some local stuff and some physical stuff, what about remote? How do we? What is there, right? Obviously, if you're talking remote in the modern world, you're talking TCP/IP, right? So you need a TCP/IP stack, and you need to have some services that you either expose or that you have client code for that you go talk to, right? And that's BootP and DHCP and DNS and iSCSI and NFS. And if you're a corp net, you probably want to have IPsec, and then HTTP and HPS and TFTP, right? And sure enough, most bootloaders have code for this. And then you start asking, okay, well, what's the attack surface? For TCP/IP, if you implement your own stack, well, A, good luck, because you're going to screw it up. But secondly, it's like, okay, well, if you look at these things, you take a step back and say, okay, well, really, this is all mostly TLV parsing. And so you go and look into what are the sort of the things that can go wrong if you do TLV parsing, and there'll be out of bound reads pretty much everywhere, and you'll see endless loops in lots of places and things like that. If you look at the protocols on top of that, like DHCP and DNS, you have sort of your standard sort of network attacks where you'll see like lease stealing or cache poisoning or things like that if you don't protect your ID. So if you have a static ID or you don't validate your IDs or you generate predictable IDs, you can have these kind of poisoning, stealing, man-in-the-middle attacks, right? And then thirdly, obviously, the thing we really like to see is memory corruption bugs. At the end of the day, you take network data and you parse it, and if you do it wrong, you may cause memory corruption bugs. Another sometimes overlooked interesting bug, I think, when you're doing network parsing is when you have information leaks. So this often manifests itself. Heartbleed, of course, was one example. It was a perfect primitive, but generally it'll be this thing where you end up generating some kind of packet as a response to something, and you'll have done a memory allocation, but for some reason not initialized something, and so you end up sending uninitialized data over the network. So this is sort of the common things you see in network stacks in general. So if you are looking for these kind of bugs in a boot environment, or if you are building a product that does this, I would highly recommend fuzzing them. There are numerous interesting network fuzzers. If you're looking for network stack fuzzing, I would recommend ISIC. It's pretty old, but it's still incredibly effective. It tends to break most network stacks. So with that said, let's show some examples. So U-boot, for example, this is the U-boot DNS code, and if you see that, that's the TID, that's the DNS ID, and it's basically they use the static DNS ID of 1 for all DNS packets that they send out. So doing DNS man in the middle on a U-boot environment is extremely trivial. You guess the DNS ID by saying that it's 1, and you are correct 100% of the time. So this is Broadcom's coffee, and this is the Dhp Parser, and it basically has this junk stack buffer where it just needs to read something out of a buffer, and it goes and says, okay, well, give me the length of that thing, and it's a uint 8, so that means it can represent 0 up till 255, and then it reads 0 up until 255 into that junk buffer. So that's a stack corruption right there. If you then look at the coffee a Tsp parser, it's very similar, where in this case it has a 512 byte buffer, and then it basically copies the entire RX buffer into it, and this is for Ethernet, so up to 1,500 bytes gets copied into this 512 byte buffer, again causing memory corruption. Obviously, we're not done with coffee yet because it has such beautiful code. So this is the coffee Icf Ping Handler, and this has this really cute sort of use after free bug, or double free, where it sends out a ping, and then it sits there receiving. You see the while loop there, and it basically sits there receiving packets until it finds the right one. But it also, because it doesn't want to have an endless loop, it has a timeout. And there's this interesting condition where if the last thing it looked was the packet you were looking for, but it also timed out at the exact same time, it frees that packet twice, which obviously can lead to memory corruption. Again, we're not done with coffee yet. Oh, right, there we go. Not done with coffee yet. So this is the IP handler in coffee. And if anybody has ever looked at an IP header, which I would assume most of you have, you'll know it has an IP header length and a total length. Of course, coffee needs to know this because it needs to know where stuff is. But coffee validates neither the IP header length or the total length. So once you start messing with those, coffee blows up really fast. So that was sort of a quick overview of all the trivial TCP and TCP related bugs that show up in your average bootloader. But let's say you got that covered, and let's say, okay, what's the next thing? What more sort of network stuff can we do? And then of course what comes to mind is Wi-Fi, 802.11. And a surprising number of bootloaders don't have 802.11. So I don't know if that's sort of on purpose, or it's just sort of we didn't get to having this feature yet, but we will at some point. And obviously it'll have bugs when we implement it. But we did find one that has it, and I'll get to that in a second. One thing I did want to mention is that if you look at 802.11 like frame parsing, depending on which device you have, and particularly which radio your device is using, you'll have radios that do a lot of parsing on the radio, in which case the stack is kind of covered because it's, or at least you hope it is, where the radio does a bunch of validation. But then there's a whole bunch of radios that sort of, they take packets from the wire and they just don't do anything and just pass it on to the OS. That's the stuff that's interesting from attack surface point of view, if you're looking to attack the bootloader and not the firmware. Yeah, we looked at iPXE, and of course, anytime you do any kind of Wi-Fi stuff, the first thing you do is you're looking for an SSID, right? This is what this thing does. And it sort of has this SSID buffer, which an SSID can be up to 32 bytes. So that is 32, well, it's 33 bytes because it's 32 plus 1. And it has this loop where it sort of goes over IEs that it gets. And then when it finds the right the IE for an SSID, it says, okay, we'll take this IE and we'll do